The topic for this recording will be how we're going to use what we call Dalton's law and calculate partial pressure of a gas in a mixture, one of our objectives for this chapter on gases, their properties, and behavior. Another of our laws for gases beyond the ideal gas law, which we've used extensively, is called Dalton's law of partial pressures. And this tells us what? The total pressure exerted by a mixture of gases in a container at a constant volume and temperature, because they're all in the same container, is equal to the sum of the pressures of each individual gas in the container. So the pressure total is equal to the sum of the pressure number of gas number 1, gas number 2, up to n gases. It can be any number of possible total components in the mixture. What we will use then is what we call a mole fraction, or X. It's kind of a funny term, but X is describing the moles of a component gas compared to the total moles in a mixture. Or so we'll say X sub I is going to be related to the number of moles of gas I, an individual gas, compared to the number of total moles. Or X sub I is also going to be related to the pressure of an individual gas compared to the total pressure. So the mole fraction will relate to either of those kinds of expressions. So think about it in this graphic or visual way here, where we have two different containers of gases. One on the left has red gas molecules, and the middle has green gas molecules, and they have pressures on gauges shown at the top. And this one has a little bit of pressure, this one has some more. But if you combine the two gases in the same volume, there's no change in volume here. On the right, now we have a different level of pressure. It's increased by combining the two gases, and their numbers of moles are combined into that last container. So what we see here is that pressure 1 and pressure 2 are combined. The volume and temperature are constant. We haven't changed the external conditions, and we put them in the same size volume. And the total pressure is the combination of the two. Now, let's do another way of thinking about these. Consider a case where you have two gases A and B in the container of the volume of V, like we showed in the previous example. And N sub A is the number of moles of gas A. And the pressure of B is going to be the number of moles of B times R times T divided by V. So it's this pressure, volume, and temperature relationship from the ideal gas law, but N sub A and N sub B then are referring to the moles of the two components in that container. The total pressure from Dalton's law is said to be, total pressure is the sum of A and B pressures. And so the pressure of A is going to be its mole fraction times the total pressure, or the number of A divided by the number of A plus B, number of moles of each. Or the pressure of B is going to be its mole fraction times the total pressure, which is the X, as in mole fraction of B, is going to be the number of moles of B divided by the moles of A plus the moles of B is this total number of moles. So the pressure of the individual gas is its mole fraction times the total pressure. Don't forget that we defined the mole fraction X sub I to be the number of moles of individual gas I divided by the total number of moles. Another way of thinking about this. Okay, so let's use it in an example. And this one is a really simplistic pictorial representation. Not such a bad way to start them off here. We have three different colors of spheres representing three different gases. We're given that the partial pressure of the blue gas is 240 millimeters of mercury. And the partial pressures of the red and yellow gases we are going to try to determine and figure out the total pressure. Wow, well, where do we begin? So we'll have to assume that the number of spheres corresponds to the number of moles. Let's just pretend it's moles. It's close enough. Or it's going to be proportional to moles. So blue, the number of blue is going to be, I should have done this with a different color. Let's do that. The number of blue, to not make your brain hurt, is going to be 4. Let's just say it's 4 moles, or 4 mole fraction. The number of red is going to be proportional to that in the number of spheres that you count there. So if you can do the counting, 1, 2, 3, 4, 5, 6 red spheres. There's 1.5 times as many of the red spheres. And then the yellow, well, what will the yellow be? So apparently there's just 2. So the number of the yellow, and I don't have a yellow tool here, so we'll just use green, is 2 moles. Now, what does that tell us? The total and the fractions. The total number of moles here is going to be 12. Easy math. We don't have to think too hard to get this kind of calculation. And so if we know that the pressure of the blue gas, the pressure of blue, oops, fix the colors here. The pressure of the blue is going to be its mole fraction of the blue times the total pressure. We're going to get us towards understanding the pressures of the other gases. The pressure of the red is going to be its mole fraction times the total pressure. And the same thing for the pressure of the yellow. The yellow gas, whatever they are, we're assuming they have no influence on each other. That's the way we assume things. Whoops. The mole fraction of the yellow gas times the total pressure. So what do we do next? So if we know that the mole fraction, we can determine the mole fraction of the blue, right? So the mole fraction of the blue gas is its number of moles divided by the total number of moles. So 4 over 12, which is 1/3. And we can put that in there to determine the total pressure. So pressure total is going to be up here from this relationship. It's going to be the pressure of the blue, if you follow my math here, divided by its mole fraction. And so we have the pressure of the blue is 240 divided by 1/3. Well, that would be 240 times 3. So the total pressure is going to be 3 times 24, which is 720 millimeters of mercury. Okay, now we're getting close. And so next we need to come up with the partial pressures of the red and the yellow and the total pressure. Well, we just got the total pressure. So, whoops, pardon me, I bumped something. The total pressure now is 720 millimeters of mercury. Got that answer. But we need to come up with the pressure of the red and the yellow gases still. We're getting closer. So let's figure out the total. We have that value and for the total pressure. The mole fraction of the red gas is going to be its number of moles, 6 out of 12. Well, guess what? That's 1/2, 0.5. And so the pressure of the red is going to be the mole fraction times the total pressure, 720. I think you can do the math. Looks like 360 millimeters of mercury. So we got that one. And now to get the pressure of the green, we have to come up with the mole fraction of green. So it's yellow. It's yellow, but it's a green tool. The mole fraction of the yellow is 2 out of 12, which equals 1/6. You can put it in a fraction, but I'm too lazy to do it. I'll just leave it like this. Pressure of the yellow gas then will be the mole fraction of the yellow, which we just said was 1/6, times the total pressure, which is 720. 1/6 of 720 is 120. If you can remember your math facts, that might be easily obtained. So now we have the pressure of the yellow gas. Is there another way we could have determined the pressure of the yellow gas? Yes, because the total pressure is equal to the pressure of the blue plus the pressure of the red plus the pressure of the yellow, and we could have done it in a different order too. But the pressure of the yellow will also be the total pressure, and subtract from that the pressure of the blue plus the red. Blue plus pressure of the red. In other words, 720 was our total pressure, right? Total pressure down here. And 720 millimeters of mercury was our total. And the blue was determined to be, the pressure of the blue is given to us at 240. And the pressure of the red we decided was 360. And so if you do your math, 240 plus 360 subtracted from 720 is which value? Looks like 600, right? And you'll get the same answer, 120 millimeters of mercury. So there's more than one way to get to that once you know the pressures of the other gases. That's one example of how you can use Dalton's law of partial pressures on an example where we don't even have much more than just a pictorial representation of gases. All right, that's kind of a fun way to do it. Depends on whom you ask. For a chemist, it might be. Okay, so the next one, we're going to do a different example. We have a sample of gas, natural gas. It's going to have some methane. It's CH4, 8 moles or something, and then about 0.4 moles, not so much, of ethane, which is C2H6, and a little even less of propane. C3H8 is propane. I'm going to put those comments in here to remind you that we've seen these before. Ethane is this one, and this is propane. So natural gas might not just be pure methane, but it's one of the major component. If the total pressure of the gases is given here as 1.37 atmospheres, we're going to figure out the partial pressure of the propane. Well, what equation are we going to use? Remember that the total pressure is going to be pressure 1 plus pressure 2 plus pressure 3. And we also need to figure out each of the individual pressures, which aren't yet given to us. But we can relate these individual pressures. Pressure 1 is going to be its mole fraction times the total pressure. And that can be applied to pressures 2 and 3. So let's just call methane gas 1. We can call ethane gas 2 and propane gas 3, which is the one we want in this case. So let's think about that for a minute, and we'll verify ourselves on the next screen. So the total, oh, I want to do the mole fraction. I meant that first. The mole fraction of gas 3 is going to be required to get its pressure, right? Because pressure 3 will be its mole fraction times the total pressure. And so the mole fraction of the propane is going to be 0.116 moles divided by the sum of the total moles. So it's going to be 8.24 plus 0.421 plus, keep going, a very small number, 0.116. And that will give you the fraction of the propane, the mole fraction of the propane in this mixture. So working out this problem stepwise, you get 0.116 moles divided by the total moles, which is 8.777 moles, and it's a fraction, so there will be no units on it. And the answer to that calculation becomes another value that we can use in our determining of the pressure. So 1.32 times 10 to the minus 2 is the mole fraction of gas number 3, in this case, propane. All right, so you can see we're getting it set up, and we're going to use that mole fraction, and we'll be able to use the total number of moles to figure out the individual pressures. So the total pressure is given, and so the mole fraction of the propane times the total pressure will give us the partial pressure of the propane. I think that should be clear to you. So let's look at it laid out in fancy form. The total pressure is 1.37. The mole fraction of the propane is those values combined and in a ratio. Okay, so why they put it in a decimal version here instead of exponential notation. The pressure of the propane then becomes its partial pressure, its mole fraction times the total pressure. So this is those using this equation to come up with the pressure of the propane. And that becomes a value of 0.0181 atmospheres, just numbers at this point. So it's a very small component of this sample of natural gas. All right, one more example then here. Let's try another of mixtures of gases, and we'll see what we can do with these in terms of partial pressures and so forth. So mixtures of two gases, the A and B, one has a mole fraction equaling 0.48, and the volume of the vessel is increased by 2, and the Kelvin temperature is decreased to 1/2. What is the mole fraction of A? So let's think about this. So if we have our ideal gas relationship, we're trying to decide what is happening to the mole fraction. In other words, the total number of moles of A, and there are two different components in this mixture. So the volume is going to be now twice the volume. So volume 2 is twice volume 1. And the Kelvin temperature 2 is 1/2 the initial temperature. And what is that telling us? Has that affected the mole fraction of A? Does it change the number of moles in the container? It might change the pressure, but it has no impact on the number of moles. So this is kind of a sneaky question. So in fact, no. The mole fraction of A has been completely unaffected by the change in the system for volume and temperature. So that concludes my discussion of partial pressure and Dalton's law. I hope you find that helpful as you work on your homework. Please ask lots of questions. See you in class.